Dear students, welcome to Nuclear Physics 1, lecture number 14. I'm Dr. Pervez Ahmed. In these lectures, we will have discussions on problems on radioactive decay. That is, we will try our level best to solve or to give the strategy for problem solving on radioactive decay. So the problem that we will deal uh, here consists on decay constants, activity, and mean lifetime. So let's start our today's lecture with the problem solving strategies. So the first problem that we will take on is basically consist on decay constant problems or probability of disintegrations. So the first problem that we have is what is the decay constant of vanadium 52, which has a half-life equal to 3.74 minutes. So we are asked to find out the decay constant for this particular element, or the half-life is given in minutes. So first of all, we have to convert that into second, and then when we apply the formula to find out the solution. So here is the formula. The basic formula for the decay constant is lambda is equal to 0.693 divided by the half-life. So this is the half-life, which is given by 3.74 minutes. So per minutes to be converted into second, we have to multiply by 1 over 60. By this mean we will have to convert. By this mean it will be converted into a second. So once done like this, then you do the multiplication. So we will get the answer. The answer is equal to 3.09 into 10 raised to power minus 3 per second. So this is the value for the decay constants for vanadium 52 with a half-life equal to 3.74 meter. The second problem again we have for the chromium 51, that is we are asked what is the decay constants for chromium 51, which has a half-life equal to 27.7 days. So again, first of all, the first thing is we have the formula for the decay constants, which is just like this one. But here just like discuss here, that here we have to we convert minutes into second. So here day will be converted into second, and then we will do the calculations to find out the decay constant. So here we have that is the basic formula. Lambda is equal to 0.693 divided by the half-life. So half-life is 27.7 days. So in order to convert that into seconds, we have to multiply this the days with what with the number of seconds that we have on one day. So in one day uh, we have 86,400 seconds. So by this mean we can convert days into second. So now the thing is very simple. You just need to do the calculation with the help of the calculator. So you will get the values for the decay constant, which is equal to 2.89 in 10 raised to power minus 7 per second. The third problem is what is the decay constants for radium 226, which has a half-life equal to 1722 years. So again, the difficult task is we will have to convert years into second, and then the formula remains the same. So just like that you have to proceed. You have to put the values in the basic formula. The difficult task that I mentioned, half-life is given in years, so you have to convert that into second. So first years should be converted into days, and then days should be converted into seconds. So here we have in one day we have 86,400 seconds, and in 1 year we have 365 days. So you do this calculation with the help of the calculator. So you get the answer 1.355 and 10 raised to the power minus 11 per second. So these three were the problem relevant to the decay constant. I mean, in these problems, we were asked to find out the decay constant. We also have the problems on the activity. So what is an activity? An activity of radionuclide is given by its disintegration rate, and this is given by A is equal to minus dN over dt, which is equal to lambda n, which is equal to natural log 2 divided by the half life. I mean, this is the definition or mathematical form or mathematical formula for the activity. Now the problems, problem number first based on the activity, that is how much time is required for 5 milligrams of sodium with a half-life 2.60 years reduced to 1 milligram. So how to solve this? We have the formula, the formula that's been derived from radioactive decay law for the activity, in terms of a mass. So it's given by m is equal to m naught exponential minus lambda t. M is the required amount of the mass, and this is the initial mass, and then exponential minus lambda decay constant, t is the half life. So now t is the time basically that's being needed. So you just put the values. The required amount is 1 mg. So 5 mg is the initial amount. Exponentials, you put the values, the given values, that is the values for the decay constants, lambda, and here is the half life. So you do the calculations. From this calculation you can get the value for the time, which is equal to t is equal to 6.04 years. So this is the required answers. So another problem, problem number 2, is that what percent of a given amounts of radium 226 will decay during a period of 1,000 years, given a half-life of radium is equal to 1,622 years. Lambda decay constant is equal to 4.38 in 10 raised to power minus 4 per years. So against the decay constant, the formula for the activity is given by A over nr is equal to exponential minus lambda t. So now you just need to put the values. Once you put the values, you do your calculations. So from the calculations, we can get this value that is equal to 0.645. If we convert that into percent, in percentage, so it's equal to 64.5%. Therefore, the percentage transfer during the 1,000-year period is 100% minus 64.5%. So that equal to 35.5%. So that is the exact amount that's been needed and what's been asked in the problem number 2. Specific activity, what is mean by the specific activity? So the relation between the activity and mass of the material is basically called the specific activity, or you can say that specific activity is given by the number of the becquerels divided by the unit mass or the volume. So this is the definition for the specific activity. We have the number of radiations that is in becquerels divided by the unit mass or the unit volume. So that give us the specific activity. So specific activity in terms of mass is equal to activity divided by the mass. So the activity is measured in becquerel and mass in gram. If we take activity in terms of the surface, so that is equal to activity divided by the area. So we have activity is measured in becquerels, area is measured in centimeter square. If we take the specific activity in volume, So it's equal to activity divided by the volume. So again, activity and becquerels, volume in centimeter cube. So that we have the definition for specific activity in term of mass, but surface and volume. So now specific activity mathematically means how we deal with the problem. So mathematically, specific activity is given by lambda n. So lambda, we just put it, and we just put the values for the n, that is 6.025 10 raised to power 23. I mean that's the Avogadro number, divided by the atomic mass, that multiply by becquerel per gram. That is, I mean, we how we calculate the activity in term of mass. So lambda in term of half life, so we put the values, that is 0.693 divided by the half life. It's a value for the lambda, and then this is the Avogadro number divided by the mass. So the specific activity is, I mean, so you just put the relations, put the values, you do the calculations, so you get these relations, you get these values. So there are more problems. I mean, that is problem number 3. You're asked to calculate, I mean, something for natural potassiums with a weight, atomic weight 39.102 atomic mass units. uh, Contains potassium 39, 93%, 93.10%, have an atomic mass 38.9637 AMU. Potassium 40, 0.0118%, which has a mass of 40 mu, and is radioactive with a half-life equal to 1.3 in 10 to the power 9 years. Uh, Potassium's 41s, 6.88%, having a mass of 40.9614 AMU. So estimate the specific activity of naturally occurring potassiums. I mean, these are the quantity given, I mean, different isotopes of potassium. So we are being asked to estimate the specific activity of naturally occurring potassiums. So how we proceed? uh, I mean, we know that specific activity refers to the activity of 1 gram materials. So here we also know that only uh, potassium 40, that is 0.0118% is radioactive. So 1 gram of naturally occurring potassium contains 1.18 in 10 raised to power minus 4 grams of potassium 40. So if we calculate the specific activity, so we have the relations that is equal to A is equal to lambda n. And for lambda, the decay constant, we have this value, and for the n's we have a specific value, but here we are not mentioning that, we just put the values directly, we have all the values. So we just put the values, you do the calculations and years, so we get this. When we convert that into seconds, so we get these values, and this corresponds to when it's converted to becquerel, so we get the values for the activity, that is equal to 30 becquerels. So I hope you know, I mean, with the help of the previous lecture, you are expert in the units. So that's why you're experts in the, I mean, you know about what is mean by n. So here we have just put the things directly for you in order to make you thinking for the basic concept relevant to the problem. So that's all we have for this lecture. Thanks for watching. See you next lecture very soon. Till then, bye bye.